How can a machine that weighs thousands of tons sink on purpose, then stop at an exact depth, and rise again like an elevator without flapping wings or firing rockets? Submarines control depth by controlling average density. They use ballast tanks to swap air and seawater. More water inside means the sub's overall density increases, so it sinks. Push water out with air, and it gets lighter, so it rises. Then, once it's close, small adjustments, plus control fins, let it hover at a precise depth. The secret is buoyancy, Archimedes' principle. Water pushes up with a force equal to the weight of the water you displace. So a submarine is basically playing a balance game between two forces, weight pulling down and buoyancy pushing up. If weight is bigger, it sinks. If buoyancy is bigger, it rises. The magic state is neutral buoyancy, where they match, and the submarine can just hang there. Weight alone doesn't decide floating. A ship can weigh more than a mountain and still float, because what matters is average density, total mass divided by total volume. Submarines are built with lots of enclosed volume. On the surface, their ballast tanks hold mostly air, keeping average density low enough to float with part of the hull above water. To dive, the submarine opens vents and valves so seawater floods into the main ballast tanks. As water enters, the air inside escapes upward. The submarine's mass increases, but its outer volume stays almost the same, so average density rises. That's the big step from floating to ready to sink. But here's the important detail: submarines don't usually want to drop like a stone. They want control, smooth, deliberate, stable. That's where diving planes come in, control surfaces that work like wings underwater. When the sub moves forward, small angles on these planes create lift or downward force. So ballast tanks get you close to the right heaviness, and the planes shape the path, descend, level off, climb, or hold. Once near the target depth, the goal is neutral buoyancy. That means the submarine adjusts smaller tanks, often called control, variable ballast, or trim systems, so it's neither strongly sinking nor rising. If it's slightly heavy, it can add a bit of air or move water around to fine-tune. If it's slightly light, it can take in a bit more water. Think of it like a scuba diver's buoyancy vest, but engineered for a steel vehicle the length of a building. Depth isn't just up and down, attitude matters. If the nose is too heavy, the sub wants to tilt down. If the tail is heavy, it tilts up. So submarines use trim tanks, tanks placed forward and aft, to shift water and balance the vehicle like moving a weight on a seesaw. Good trim means the submarine can cruise level, waste less energy, and hold depth with small, smooth control inputs instead of constant fighting. To surface, the submarine reverses the density game. It uses compressed air to push seawater out of the ballast tanks. Less water inside means lower mass, so buoyancy wins and the submarine rises. In normal operations, it's controlled and gradual. In emergencies, subs can do a rapid blow to get positive buoyancy fast, basically telling physics, we're going up, now. Holding a specific depth is a constant balancing act. Water density changes with temperature and salinity. The submarine's own volume can change slightly under pressure. Even speed changes how the planes behave. So the crew and onboard control systems keep making tiny corrections, a little trim here, a little plane angle there, a little ballast adjustment. That's why submarines feel less like sinking and more like flying in a heavy, invisible ocean sky. So ballast tanks handle the big change, air versus water, while trim systems and diving planes handle precision. It's not brute force. It's controlled density, careful balance, and constant small corrections. Now your turn. What should we explain next? How submarines steer without a rudder like a plane, or how they communicate when radio waves can't reach them underwater.